Okay, recording started. And yeah, welcome again to another computer vision study group session. I don't know if any of you has been here before. Yeah, so in general, I talk about papers. So it's an open study group, by the way, right? So if you have papers, we had some people in the channel that said like, oh yeah, I would like to present the paper. So feel free to just reach out and then we, schedule some date and talk about it. Yeah, so the way I do it mostly is first presentation style, but yeah, if you have questions somewhere in between, really just whenever, just yeah, say something, write in the chat, and we'll talk. So today the topic is the FlexiViT paper, right? It's called FlexiViT, one model for all patch sizes. It's still quite a recent one, right? It was released in December, I think 5th of December last year. So not even 2 months old. And it comes out of Google Research. Yeah, so basically the people that also created the original VIT paper. And as is usual to my presentations, I give them a theme. And today's theme is, wait a second, a medieval one. So, and the first thing I always do is a little intro that has a loose connection to the paper, I would say. And is fitting a theme. So for this one, I prepared the tale of Sir FlexiViT, right, to get you in the mood, like the medieval thing. Yeah, and I just start with it. So this is a tale of Sir FlexiViT, who struck all monsters as he saw fit. Our story begins in an old castle deep in the land where the stones lie asleep. The old stronghold stood mighty and tall, loud and clear rang the angry king's call. I'm losing my treasure, I'm losing my land, all of you fools sit waiting for gold in your hand. He roared angry at the knights in the round, in all of his kingdom none better were found. All different and still all the same, all masters of their professional game. Monsters to slay was their daily métier, and all sizes and colors they came every day. Monsters so brutish and big as their dump, others small, canny, not stupid, not plump. The knights they matched them so very alike, some slower and rough, some quicker to strike. No big knight could strike a small cheap cheeky imp, no small knight withstood a dragon's big wing. Thus the king had hired a horde of the best, each singer had passed their personal test. But now he laments as the knights are so many, and costs they keep rising, he counts every penny. The same day a stranger knocked at the gates, ready to lift the king's grimmest fate. No sword, no armor, no gold in his hand, he looked like a peasant from the innermost land. Hand me a weapon and a knight-worthy horse, so I can slay monsters from south to the north. The king, devastated and in great despair, gave him a blunt sword and a scraggy old mare. Months they had passed, they all thought him dead, when over the wall came a dead dragon's head. An imp, a troll's eye, a serpent's long tail, nobody thought that the man would prevail. Yet there he stood, all covered in blood, dirt in his hair, pants, shoes full of mud. I slayed them all for you in different size, I care not their species, now I want my prize. The king was delighted, invited him in, announced him a knight for his special kin. From this day on he was known as Sir FlexiViT, who struck monsters all sizes as he saw fit. All the other knights they were let go, the king cast them out without much ado. So if you face a monster tall as a mountain or small as grass, fear thy not, for Sir FlexiViT will save you at last. Okay, this was mostly me having fun, and you might wonder, okay, what has all this to do with like a scientific paper about machine learning, right? Yeah, so let's say Sir FlexiViT who slays monsters of all sizes, that is in a way connected. Um, yeah, and by the way, the images right there all created with Stable Diffusion, so I spent a lot of time uh, finding the right, yeah, settings and the right prompts to create nice pictures with stable diffusion, so I don't have to credit any people here. Yeah, and that was the intro. Now we get to the real paper, right? And maybe a bit more scientific. So that's the paper. You see it here, like the first page of the paper. Um, so what I found interesting about their design choice on the front page is that they actually put two figures right here, and then their abstract is down here, right? So it's already quite visual. And I mean, they put cute koalas on the front page, which is not wrong in any way, I guess. So they probably get some cuteness scores with the koalas from the reviewers, like, oh, they have koalas. That's really nice. Um, but yeah, apart from that, it's not much special about the design of the paper. It's a two-column style, you can say, right? Because sometimes you have one column, two column. Um, but that's not that interesting, right? What's more interesting, of course, is the content. But first, let's have a look at the vision transformer, like a little recap on the original vision transformer. What is it? As I said, a lot of authors from this paper were involved in this original vision transformer thing. And it was released in 2021. And yeah, it was one of the first vision transformers that really could hold a candle to convolutional networks in some tasks like classification. And ever since then, it's been the base of a lot more yeah, transformers that deal with vision, the backbone of many. And I just want to do a little recap on how does it actually work and what's the problem with it? Why do we need FlexiViT, right? So let's start really from the input. So let's imagine we have an input. Thematically, it's a dragon, right? But because it's not that good for visualization, I pixelized it quite a bit. So now basically we have an image that is just pixels, like 8 by 8 pixels, right? In total, 64 pixels. And what we do now for width is, yeah, here's like the pixel grid. What we do for width now is we say, okay, we split those 8 by 8 pixels up, and we can actually choose how we split them up. So it should be in squares in this case, but yeah, we can do this like 2 by 2 patches, right? So it's 4 patches in total. So up here, in every patch we have 4 by 4 pixels. Okay, and that's where we have to talk about uh, some terms, because it can get quite confusing. When we're talking about the patch size, we're actually talking about how many pixels are in one patch in one row or column, right? So we say the patch size here would be 4, okay, because here it's like 4 by 4. Patch size is 4. When we talk of the grid size, again, we talk of the token grid, basically. When you say the grid size is 2, then we mean 2 by 2. So grid size is 2 by 2. And when we speak of the sequence, that's the number of tokens in the whole image, right? So the sequence length would be 4, because we have 4 tokens here. Okay, so we have patch size, pixels, and we have grid size, which is the number of tokens basically, and then we have the sequence length, which is the total number of tokens in this thing. Okay, yeah, I'm just saying this up front because I get confused by it myself sometimes when they're using these terms in the paper. Sometimes you're like, hey, what is it now? And yeah, so now we're all on the same page, I hope. And you can start. So what you do in the vision transformer, the original one, is you take these tokens, these patches, and feed them into a linear projection layer, which then gives you 4 embedded tokens, basically, or embedded patches. That's what you say. You can say they're tokens, and they're just these embedded patches, right? So usually it's like a convolutional layer here, and that's just embedding you some patches, and then you get, in this case, you get 4 tokens out of it, and you add 1 class token to the front, and then you give all of them their positional embeddings, right? So you add the positional embeddings to them, so 0, 1, 2, 3, 4 in this case, and then you take the tokens and their embeddings and feed them to a transformer encoder, which is just a standard transformer encoder basically. And this one then gets an multi-layer perception head, for example, from which you can then classify whatever. So in a classification case, right? Then you can say like, okay, now we can classify our Imagenet dataset or whatever you have trained it on. For today, for the FlexiViT, we don't care about most of the part that is in the end. We care about this part, I would say, right? A lot of the patchification and a bit about this embeddings stuff. Okay, so next slide. Let's talk about the patch size, right? I already said like, okay, patch size, that's the number of pixels here. And we say when there are more patches, so when the patch size is actually small, right? Because when patch size is small, we have more patches. Then we can get a higher accuracy on many tasks. That what experiments showed, right? So now we have a smaller patch size, more patches, and this gives you, especially on classification, it showed like higher accuracy. I suppose it's because you can cover more details by it, right? Because when you have patches like this, I mean, yeah, they all get lumped together in a way, all the pixels here, and then you calculate the self-attention between these big patches. When you have smaller patches, you just have more information, I guess. But it also comes with the trade-off that you need more compute because now you have to compute more self-attention, right? Because before, I mean, there's just 4 tokens to compute the self-attention between them, and now you have like 16 tokens to compute the self-attention. Yeah, it actually scales with s to the power of 2, with s being the sequence length, so the total number of patches. Yeah, so that's how this self-attention scales. But what you can do is you can actually vary it, right? So when you say, okay, for pre-training, I want to use the patch size 8. So you have like the bigger patches, patch size 8, right? Because it's just easier to compute. We don't need that much resources for pre-training. And then we actually fine tune on the smaller one. That works, right? You can do that. It's not as good as completely doing the pre-training and fine-tuning with 4, for example, but it works. So next size. So the problem is that when you try to change this patch size during inference, then you can actually see quite a big decrease in performance. So this figure already is a bit of a spoiler because it shows that the FlexiViT thing is performing quite well. What we see here is the Imagenet Precision score on this axis, right? And down here is the inference time sequence length. That's actually, I think they got confused here a bit as well when they say sequence length and patch size. Because, I mean, the sequence length is not equal to the patch size, as we just discussed, right? So I think they mean the patch size actually down here. So here the patches are bigger, right? 48, when that's the patch size, you have big patches, and when 8 is the patch size, you have small patches. So here's a higher accuracy, as you can see, right? Accuracy increases when the patch size gets smaller. So actually the sequence length increases, and here it's decreased, but yeah, let's not get lost in that. And what you can see here is a original virt model trained on a patch size of 16, right? These bigger lines here. And that actually also peaks in accuracy at patch size 16. And when you change the patch size, then it decreases, right? So it's not that good to really, change the patch size at inference time. And the same for this VIT, which is trained at a patch size of 30. It also decreases, similar to the one at 16. Yeah. So the FlexiViT doesn't decrease that much, as you see. But why, we will see later, right? So first we've got this problem of, okay, we change the patch size and the whole performance decreases. But why is that, right? So now we come to the crazy Mast part of the paper. I took a bit of time to get through it. They have a bit of their notation, and I think I will just quickly cover that. I mean, if you're really interested in the Mast part, we can also have a look at the code later on, because it's easier to understand with code really than just to go through it here. But I quickly try to explain their motivation or their thoughts and what they do to solve this problem. So let's assume we've got a small x here, which is the patch, basically with the shape of p times p, right? P is the patch size. So we have a patch of 4 by 4 pixels. Then we've got W, which in this font just looks like an upside down M, but it's a W. And this is the patch embedding weights, which are also the same size, right? P by P. And then we've got this one here, which is the dot product of the patch and the patch embedding weights. Okay, that's this term. And then we've got an operation, which is called resize to star p y, right? And that means we just resize y to star p. For example, when there's 2p, means we resize y to double the patch size that it was before. Okay, now to the problem, right? So we've got our dot product of the patch and the patch embedding weights here. And then when we compare it to a resized version of this dot product, right? So we resize our patch to double the patch size, and we also resize the patch embeddings with it to match it, right? Then we can see actually that the dot product, or they say like the magnitude of this dot product, is only a quarter of the original, right? So it's quite a drastic change in this magnitude. And they are saying they assume that might be a reason why this performance decreases. But they also don't say like, yeah, that must be the reason. They say like, probably that is the reason, and we are trying to make it better. So that was their motivation. It's a bit like, yeah, maybe it is, and we just do something to make it better. And in the end, well, it got better, so probably they were a bit right about it. But yeah, their formulation about it is a bit vague. So they ask themselves, right, are there better ways to resize this whole thing so this magnitude doesn't change as much? And then we get to the next crazy Mast part, where we have another dragon doing Mast over here. Now we have W hat, which is the new patch embedding weights, and we have B, which is a resize matrix, right? And now they say, okay, we want to optimize this thing here. Yeah, so that actually, yeah, the magnitude is not changed that much, right? So what you see here is the dot product again of the original, and then you see the dot product of the scaled version, basically. Then they, well, get the difference, and of course they want the difference of these two dot products to be as small as possible. And they say in the end the solution is the pseudo inverse, which is denoted by this one, so the pseudo inverse of this resize matrix, right? The whole derivation, everything, if you're interested in it, you can have a look at the paper. They give the whole derivation in the appendix. So in the end, they just say, okay, we've got our pseudo inverse resize, and we've shown that it's better than just plain bilinear resizing it. Okay, so that's their solution to the resizing problem. And it also shows, for example, here, right, they've got a comparison. Okay, we've got a pseudo inverse resizing, and down here they've got like input image size and the patch embedding size. And it shows that when the images get bigger and the patches get bigger or smaller, then you can see actually that the performance is quite good on the pseudo inverse resize. And for example, for the vanilla resize, it's oh, it's actually better when it's it's on smaller images, but when you're on bigger images, the vanilla resize is just somewhere down here. Yeah. So what they used here was a bit B at yeah, at 8 uh, patch size. Yeah. So that's where it was trained originally, at this patch size here. And then they just try to resize it in different directions. And yeah, you can see especially for getting bigger, the pseudo inverse resize is pretty good. For getting smaller, oh, it's up to a point, it's still better than the other versions of the resizing, but yeah, it's also not perfect, right? Anyway, they use it. But of course, they do more, right? I mean, it's not their whole contribution to just come up with some new resizing method, and then that's the FlexiViT, because we've seen this koala picture, right? And it's not just resizing. I mean, resizing is part of it. You can see it here. You've got your patch embeddings and your resize, so that's then the pseudo inverse resize you do. And yeah, so they also have shared weights between these FlexiViTs on different tokens, different patch sizes. Sorry. So how do they do that actually, right? And they've got one more thing that is helping them to, not having to retrain the VIT actually for different patch sizes and still being at a really great accuracy. And it is actually quite a simple thing when you think about it, because so at training time, they just say, okay, at batch 1, we just take this patch size. At batch 2, we take this patch size. The next batch, I don't know, we take another patch size again. Batch 4, let's just use this patch size again. So they're randomizing the patch sizes they're using for each batch during training, actually. So they're just throwing in whatever patch size the algorithm comes up with, and they also give a pseudocode for that. You can see here it's really just some NumPy random choice. Then you give it an array of possible patch sizes, and for each batch it just chooses a patch size, and then you have your random patch size training basically, and that is quite effective. So it's interesting to see that like this simple idea is that effective on flexifying the bit basically. So there's a bit more down here. So I mean, here you can see like what happens during the batch, basically, right? And then here's the class itself, the vid. And there are not many changes actually to the original vid. But one thing they do is that they say, okay, we define like this fixed shape of our weights, which is 30 by 32 by 32. That's for the patch embedding weights. So that's like the starting point always, right? And then they resize it according to the patch size. And for positional encodings, it's similar. They also define like this shape for positional embeddings, which they say is 7 by 7, and then they resize it. The little difference here is that they do resize the weights with their pseudo inverse resize, but for the positional embeddings, they say like, it doesn't matter. Oh, sorry. It doesn't matter which resize you use. You can just use the standard bilinear resizing. That's good enough for the positional embeddings, right? And also for these numbers here, 32 by 32 and 7 by 7, funnily they say like, actually in our experiments it didn't really matter. So they tried a range of values, and it didn't really matter which one they chose. They just then chose like these ones because they liked it or whatever. But performance-wise, it doesn't really matter if it's 32 by 32 or 12 by 12 or what else was there? I think 24 by 24, 48 by 48. You can basically choose anything. So to flexify like your standard bit when you have like this model. All you have to do really is implement this stuff here, right? So I can quickly maybe show you in the one. So so there's this one pull request in the official Big Vision repository on GitHub. It's called open sourcing of FlexiViT, right? And then you can find some files about it. And well, the most interesting one is down here. This is Flex in project models project FlexiViT with Pi, and then you can basically see what they modify uh, in the VIT to make it flexible. So here's the whole like class of the VIT model, right? And that's the code they use for it. Um, yeah. Here's also the pseudo inverse resize. It's called resample batch embeddings. So that's the whole pseudo inverse resize. If you're interested in how that works, that's the method for it. And yeah, here's the patchification thing. And you can see here these fixed sizes of the position embeddings and the patch embeddings. Actually, so 32 with a rule and 7 by 7, right? So if you're more interested in the implementation, you can go through this pull request. I also put it in the slides, so you can have a look at it. Okay. But there's one more thing they're doing, and that is a more common thing is knowledge distillation, right? Just a quick thing about knowledge distillation. I'm not an expert on it. I think I've actually never used it really. I read up on it a bit. And so, for example, we've got an image and we say, okay, we want to classify it. Then we have two models, actually. One which is a bit bigger. We say it's a bit B6 here. And then we've got our model which is a bit smaller, which is a FlexiViT B. And naturally, the performance of the smaller model is a bit worse than of the bigger model, right? So now we want to improve the smaller model by comparing, you could say comparing the output with the one from the bigger model, right? So we say, okay, we've got this image now, you both get the image and you can classify it. Okay, so the bit B6 says, okay, that's a horse. The FlexiViT says, oh, I think it's a knight. Well, actually, it's a horse, as we see, right? So this prediction was better. And in the end, you take both outputs and distill them, right? Distilling in this case means they have this distillation function. In this case, it's a Kohlberg-Leibler divergence. That they explore in another paper. They say like, oh yeah, this one is working pretty well, and also what is important for our knowledge distillation is that the picture we show to both models is really the same. Because there's this method where you just already like give all the pictures to the teacher model and then you just save all the outputs. So it's kind of an offline knowledge distillation. But they say like, no, it is quite important to really do it online and to really give the same pictures to these two models. And they also use like heavy what's it called, augmentation, heavy augmentation on their input images. And what they also say is that it is important to train them for quite a long time. So I mean, not only the student model is really trained in this case, right? So the student model is adapted to match the teacher model. And over here they also show that so they first did it for like 90 epochs. That's this green line here. And then they did it for, I think, well, what was it, 100 and a few hundred more epochs, and it keeps increasing, right? So these ones here are the longer epoch runs. It still got better. And yeah, this is this fun match paradigm, right? It's patient and consistent. And what is quite nice about this whole thing is that when you initialize the student model, in this case, you can actually use the parameters or the weights from the bigger teacher model because they are so similar. And even though the patch embeddings or the patch size was different here, it doesn't matter for our FlexiViT, right? Because it was trained flexible. So it can be initialized with these weights, and this is quite beneficial. Some papers have shown. Yeah, it just helps in training it quicker. And yeah, we can do that here. So knowledge distillation is that. Okay. Another part of the paper is where they look at internal representations. That's actually a part I really like. So they say, okay, we looked at different blocks of our models, right? And then we visualize it with this centered kernel alignment, mini batch centered kernel alignment, where you can basically see, okay, we have different grid sizes. The size of each dot refers to like the grid size. And you can see that the grid sizes of the same block are quite close together here, so that the representations in the different blocks are quite similar actually, even among grid sizes. It diverges a bit when it comes to this one, which is about block 6 MLP, right? So it goes all somewhere else, like these grid sizes hang around here and these grid sizes around here. But interestingly, it does get together again in the end. So in the last layers, it again, like, yeah, goes closer together after diverging in between. So yeah, it shows that across grid sizes, the representations in the last layers are very, very close together. And they also had this cosine similarity between class tokens here that they did, and that shows that class tokens in all the blocks are actually quite close together across grid sizes. Yeah. Okay, so that is like some FlexiViT stuff, but now you might wonder, okay, but can we also like use it, or how good is it in usage when you use it for like classification, panoptic stuff, image to text retrieval, image segmentation, right? Or here is object detection. So what they're doing here is they take two bits with fixed patch sizes. So you see like the B30 and the B16, and then they take a FlexiViT B and they fine tune it on these tasks with fixed patch sizes actually as well. So when they do the fine tuning of the FlexiViT, here they say, okay, we also fix the patch size to 30 and here to 16, right? And then they fine tune it. And they show that, yeah, it does actually match in most cases the performance of like this static bits. In some cases, it's a bit worse, but mostly it matches, sometimes even better, like here in the panoptic case, right? But in general, so you can use it to fine tune on a fixed patch size. That's good. um, But what is also great that when you have fine-tuned it, so here you can see like this is a fine-tuned FlexiViT in green on this input grid size of 8 by 8, right? So you have 8 patches by 8 patches. And then you want to scale it up with a bit B30 that wouldn't work really well. So it would just like rapidly decrease in performance and accuracy in this case. But for the FlexiViT, you can actually also change the input grid, even though it was fine-tuned on this 8 by 8. It doesn't really matter, right? So you can still use it for other patch sizes. That's quite nice. Yeah, over here it's similar, right? Okay, so that is when you have like, yeah, when you fine-tune with fixed patch sizes. But they also experimented with flexible fine-tuning, right? So even when you have like your pre-trained VIT B30, they thought about, okay, what if we then fine-tune it with flexible patches, right? So they applied this whole training procedure with the random patch sizes and everything, and this might be the even more interesting case. So they're saying, okay, let's take a bit B30. You can see like the standard performance here. So that's when in the VIT B30 is just like this, yeah, normally trained or fine-tuned, and you get accuracy somewhere around 79 something, right? And now they say, okay, now we have our Flexified VIT B30, so they take this as pre-training and then fine-tuning with the FlexiViT method, and it actually shows that it's working quite well as well. So when you then go to a 16 as patch size, you get a better accuracy. It decreases again when it's at 8. But okay, so it does work actually to flexify a formerly static bit. So you can do that, and then it will most likely be a better performance when you resize your patches, right? Yeah, and it's similar with the other ones here actually. So again, that's image to text retrieval, that's the object detection, and yeah. Okay, then they have some more ablations, which are also interesting because I talked about this PI resize and that they're not really sure that this is really helping them. But it seemed like that in this one figure that I showed before, right? But there's another figure in the appendix that made me a bit like, huh, does it really make sense? Because here, that's their figure. They put it in the appendix, so they didn't really hide it or anything. And you see different resizing operations here. And yeah, we see, again, Imagenet Precision and the patch sizes down here. So we see when there's big patch sizes, so that's like big patches, right? Then yeah, everything is quite low, and it's all quite close together, I would say even. So when you see the PI resize here, it is a bit on top of the others when you have these big patches, right? Small grid size, big patches. So PI is a bit on top, but then, well, even this vanilla, and vanilla they mean like bilinear resizing, is still quite good with the FlexiViT here. So it's a bit like, okay, so why did you really introduce the PI resize? So they're saying like, yeah, it does have some other advantages which we show in the text, and there are some, but I feel like, okay, if you don't want to go through the trouble of implementing this PI resize or copying their PI resize, then you could just as well go with the bilinear resizing, really. Yeah, that's at least my feeling after seeing those figures and being like, yeah, okay, the PI resizing was a nice mathematical experiment from their side, and they can use it, but I don't think that it will be adopted in a lot of other architectures. But maybe I'm wrong. Maybe I'm just missing some vital points here. But that is my feeling. So yeah, and there's another ablation. Yeah, this is about these fixed shape sizes, right, of this positional embeddings and the patch embeddings. Yeah, so here you can see again where we have the patch embeddings at different fixed sizes, like this 30 by 32, which they choose in the end, but also 48 by 48 and 12 by 12. And then they again compare it, and they're quite close together. And I mean, here they're really saying, like, okay, it doesn't really matter, right? In your implementation, you can also choose 48 by 48, and it will still be quite good, right? And same here for the positional embeddings. You can also choose like your fixed positional embedding size of 14 by 14, and it will still be quite good. And yeah, that's basically it, I think. Yeah, that's the end. Okay, thank you for being here. I hope you got an idea of what FlexiViT is about. So in my opinion, it's mostly about randomizing your patch sizes at training time. Um, and then, yeah, resizing these fixed embeddings that you said before. Uh, so it's actually quite an easy idea, and as I've shown you in the code, right? It's not that much of code. Okay, it seems a bit more here, but that's because of the PI resize. It takes quite a bit of space. But the changes in the model itself are really like minimal, I would say. And that's so great about the paper that you can actually adopt a lot of backbones, and you can even, just as I've shown, just fine tune your pre-trained bits with this flexible training approach, and then it's more flexible to different patch sizes. So it's quite a nice thing that they showed here, and it's one of these rather simple ideas that works really well. Well, in the paper they they made a lot of other experiments, right? So they did this and that and this. Um, they show a lot of stuff, and so out of this simple idea, they made quite a big paper and an even bigger appendix, I would say. So they get in their numbering, they get all the way down to the letter Q in the appendix. Yeah, but it's quite interesting what they put in there as well. So that is it. Thank you. Here's some credits and the link to the PR actually, right? So maybe this slides, if you wonder, this theme of the slides is actually like, it's called the Feast of St. Louis, and it's from the Slides Go website. Yeah, and that is it for today. Do you have questions?
Hi, can you hear me?
Yeah, I can hear you.
So I kind of missed the part how they basically um taken the variable variable sequence sizes of patches, right? So the first of all they create embeddings from the patches. So if there are variable number of patches, how do they pass it through the VIT encoder? I mean, is there a linear layer that dynamically changes its weights so that the VIT encoder can share the weight?
So you mean
Like if the patch embedding is can have variable sizes, right?
yeah,
Let's say it could. Then how does it pass to the VIT encoder? Because VIT encoder takes an embedding of fixed size. And
yeah.
what does FlexiViT do in this case?
Okay, maybe we can have a look here in the code actually. Maybe that's um. So what they do, I mean, wait, where's the encoder part? Down here's the encoder, right? And they
Yeah.
take as input um, oh, the x. Okay, let's do that backward, right? So
Yeah.
x is concatenated here with a class token. Yeah, okay, that's not that important, right? Here they put the position embeddings through it. Okay, so the position embeddings probably already need the right size. Um, I mean, uh, I'm trying to figure out where exactly the important stuff happens.
Do you mind if I offer an explanation to
Yeah,
this?
sure, you can do this.
So with transformers in general, to my understanding, how they work is you can just feed them a input sequence of variable length, and then this input sequence will also have like a particular dimensionality, I believe. So in NLP, you'll like have an embedding space with different words being associated with different embeddings. Whereas with vision transformers, you'll have like these patches, and then how it's implemented is you have this like patchify layer with the and it has a convolutional layer that takes it in the image, and then it has a stride of the patch size basically, and then what this is doing is it's resizing the weight matrix of the convolutions, I believe. But the convolutions will always output the same dimensionality, and the dimensionality of this output remains constant for the entire model. So that doesn't have to change. And then what the patch resizing will do is if I like have a model that has like 16 by 16 patches, that will have a fixed input sequence length. However, if I change the patch size, it will have a new input sequence length, but the transformer is able to deal with that um, different input sequence length without issues.
Yeah, I got. So the change happens in the conv layer that creates the patches,
Yeah,
not
the
the encoder.
changes in the comp layer. The
Mhm.
remainder of the transformer is fine, and it'll just handle the output as is.
Okay.
Cool, thank you. Okay, any more questions, remarks? No, not for now. Or then,
Uh,
yeah?
I mean, for me personally, with this paper, I think the most interesting part is in Appendix K, actually, where it talks about the shape and texture bias of FlexiViT and just, I guess, visual transformers in general. I'm not sure if you're familiar with the paper that it's citing, but it's talking about how there was a study in, I think, 2018, where a couple of researchers were toying around with, I believe, ResNet 50 and investigating how it's like texture biased versus humans, which are shape biased. So, like, if you pass in a textured patch of like tiger fur, it will say it's a tiger, whereas a human will be confused. And then if you, um, I think, textured the outline of a cat with tiger fur, the ConvNet will say it's a tiger, whereas a human will say it's a cat. So that's kind of the texture versus shape bias. And this paper, I believe, is one of the first to actually look into vision transformers with this. But they do end up at the conclusion that vision transformers are shape biased compared to texture bias in ConvNets, which I think is interesting. And I guess probably just because it has to do with my own work, but I think that's one of the more
Yeah,
notable parts of this paper as well.
yeah, that's interesting. It also reminds me of the How Do Vision Transformers Work paper. I don't know if you've read this, because they also explore this topic a bit. And they also came to the conclusion that vision transformers are more shape biased than convolutional networks. Yeah, actually. But
I
yeah,
haven't seen that. Thanks for
okay.
letting me know about that.
Yeah, no worries. As I said, the appendix is quite long, so you can really, I think, discover a lot of stuff in there. So it feels like they did a lot of research, a lot of experiments actually, and they wanted to put it all in the paper. But then again, they didn't want it to be the main part too long, and so they just did a big appendix. But yeah, they have interesting ideas. Um,
I think another issue with this paper, though, is it's even though they say that the implementation is only 3 lines, I think in reality, with how, at least for PyTorch image models, that library, the way some of the stuff is structured makes it actually difficult to implement the dynamic resizing. I recall the maintainer was like having issues with that. So I'm kind of curious as to how practical this is, just as in use. Because another thing, because in the paper, when they're calling the forward call of the vision transformer, in addition to passing in the image size, they also try to pass in like a weight, or not weight, sorry, blanking on the term, patch size.
you mean a
So I think
pseudocode or something? Let me see. Where was it? Oh, wait. Oh, that was here.
yeah, this. So I think there's potential that that'll interfere with some downstream implementation of this actual strategy.
Okay. Yeah, interesting thought. I haven't thought about it actually. um, might be. Yeah, I'm also curious how much this will actually be adapted this way, especially also for new transformers, maybe, or like for new bit-based things, right? So how important is this flexibility in the end to people? Yeah, I guess we will see in the next months. So yeah. Okay, well then, thank you. I will stop the recording.